Hello and welcome to the University of Manitoba's Resources for Agricultural Engineering podcast. I am your host, Uduak Edet, an agricultural research extension engineer in the Department of Biosystems Engineering. This podcast is your gateway to discovering the latest innovation, research, and practical solutions in agricultural engineering. Our mission is to forge meaningful connections with the agricultural community and help farmers address their engineering needs and aspirations. Today, I have the privilege of speaking with Dr. Qiang Zhang, a professor of biosystem engineering at the University of Manitoba and a registered professional engineer in Manitoba. Dr. Zhang is an expert in agricultural structures and environment. His research focuses on controlled environments for animals and plants, as well as grain storage ecosystem. Dr. Zhang is widely recognized for his contributions to agricultural and biosystem engineering and has served as a president of the Canadian Society for Bioengineering and actively collaborates with governments, industry, and international partners. Beyond his research, he is a dedicated mentor and educator whose commitment to excellence has inspired generations of engineers and enrich communities far beyond the university. Dr. Zhang, before we discuss your research, can you please share a bit about your background and what first sparks your interest in pursuing graduate studies in agricultural engineering?
Hello, everybody. Thanks, Uduak, for that nice introduction. I grew up in China, my hometown, southeast part of China. And after completing my high school, I actually went to work on a farm for 3 years because all the universities were closed in China. So then I went to university and finished my undergraduate program and then went to Penn State to US actually to complete my master's and the PhD. Now, what inspired me into ag engineering? I don't have a clear answer for that because I was assigned to the ag engineering program when I was in China. But I do have 3 years of sort of experience working on a farm. I was joking with the people because the house I lived in for 3 years actually is next door to a pig farm. So that's how I got connected to pigs for the rest of my life. So that's sort of my brief background. Not too complicated.
Thank you so much. How did that path lead you to join the University of Manitoba, specifically Department of Biosystems Engineering?
When I finished my PhD at Penn State in the States, and I was looking for basically a postdoc position for 1 year. One of my major professors actually was on sabbatical at the University of Manitoba. And he sort of introduced me to the former department head of Biosystems Engineering, Dr. Ross Bully, and told him what I'm interested in. And Dr. Bully actually introduced me to Dr. Bill Muir, who's actually well known in the field of grain storage. Now, that's sort of the logistics part of it. Now, what I'm really interested in actually is the grain storage, because my master's and PhD are focused on grain storage structures, the mechanical properties of grain. There are only actually very few universities in North America that offers research program in grain storage area. University of Manitoba was one of them, or is one of them, and also Penn State. So that's how my connection sort of established. I actually met Professor Ron Britton at SABE, who's actually another senior professor in the department. So because we have the same interest in grain storage. That's sort of how I got to University of Manitoba.
Interesting. What challenges did you face as a new internationally educated faculty member, and how did you overcome them?
Well, the way I want to put it is, if you enjoy doing something, there's no challenge. I didn't feel like there was anything like challenging. Research, you put your minds to it, get things going, and it's not really challenging task. The only thing I would think of challenging actually is the teaching part, because as a sort of immigrant, you have different culture background. That actually affects your teaching. I still remember the first class I taught was to agriculture students, and I sort of followed my undergraduate teaching experience. So that didn't work out. So that was a challenge. I have to modify my teaching style to suit the culture aspect of the education. So that's a big part of that.
What inspired you to pursue work like a research program in agricultural structures and environments, specifically controlled environments for animal, plants, and grain storage ecosystem?
I got into this program. It was not by my choice, but I really
Yeah.
enjoy what I was working on, because when I actually first went to Penn State, my interest actually was soil mechanics, like the tractor driving on in the field. So that was my interest. So when I went there, there was no one actually working in that area, because that was sort of the old area. So I picked up grain storage, and then I find out there's actually common elements between the soil mechanics and the grain storage. So specifically, I was looking at the mechanical properties of grain, which
Okay.
actually is just as complicated as soil. When I started my master's degree, I look at this whole problem of grain, how it deforms when you put the load on it, and how it behaves when you put it into the bin.
Yes.
And then I noticed very few theories out there, but I look at the soil mechanics. There's tons of theories there, started about 100 years ago. So then that's how I started my master's and PhD research. I actually took the theory from soil mechanics applied to the grain storage. The more I got into it, it becomes more sort of interesting, because I looked at the fundamental properties of grain. I said, well, this is something I really want to spend my life actually working on it. Now, obviously, that is the grain storage is a pretty narrow area. In agriculture, there's a broader area of structures and the environment is sort of connected together. Grain storage structure is part of the structure part of the structures in the environment. But my major professor actually was working on both structures and the environment. I got exposed to the environment part, and then I look at, oh, this is just as interesting as the structure. In my first sabbatical I took, I went to Iowa State, and they have a large animal environment program. So I got into that. I said, I want to start another research program in this particular area. I was working with the little piglets and then looking at the heating requirement of that. It's fascinating. We actually developed a very nice program in that area. That I got into grain storage structures for my master's and PhD, then got into the environment part actually through my sabbatical.
Let's look at your research program. I know you've touched on it. Can you discuss about the development and the objective of your research program, the one you actually established in the University of Manitoba?
Well, when I first came here, and I was working with the Dr. Bill Muir on grain storage. So that's sort of the stuff I did at Penn State. I continued on with that. So I looked more in depth into the grain properties and the mechanical behavior, the grain storage structures. And as I said earlier, so then I went to Iowa State. I started a new program in animal environment, controlled environment area. When I came back from Iowa State after sabbatical, there was actually a total change in agriculture landscape. So a little bit background is the subsidies for grain transportation by the government was taken away. A lot of investment went to pig production, but that creates a problem. That's sort of the first project I sort of started with in animal air quality area. So I moved sort of from the controlled environment to odor, which is all part of the environment. So I started an odor program, and that actually sort of led me to more into air quality, and later on from air quality to airborne disease transmission. And lately, I moved from the whole airflow things to smart vertical farming with the digital technology. If I look at the sort of milestones, so the grain storage, animal controlled environment for animals, and odor, airborne disease transmission for animals, then the smart vertical farming. It's all connected because the fundamental principles are still the same. We're basically looking at the heat transfer. We're looking at fluid dynamics. We're looking at some interaction between biological systems and physical systems. The only thing new now is at the later stage when the digital technology came along. So that's how I moved to the smart vertical farming.
So which of your research contribution do you believe has the most impact on industry, academia, or the society?
This is a sort of difficult to measure. Some people measure it with publication. I don't do that. I'm looking at more, if I did something, the industry likes it. They adapted the technology or the knowledge I developed. That's the way I want to measure it. In the grain storage area, some work we did, that actually has been adopted by some standards, like on the particular loading conditions. That affects part of the grain industry. So the one I'm interested in is on a structure like grain bin manufacture. Or in the animal environment area, I think the work I started with Professor Hongwei Shin at Iowa State on heat pad for piglets. So that actually has a huge impact on the industry. So in old days, farmers used infrared lamps for heating pig farrowing facilities, but now most people actually use heat pad. We actually did a lot of fundamental work on the heat pad, how big the pad is supposed to be, the surface area, and how much heat actually is required, and what temperature is required. We did all that work. It's used by the industry. The other project on the controlled environment area is the energy efficient greenhouses. I worked with the Manitoba Hydro to actually looking at sort of energy efficient greenhouse facilities. And that project actually has a lot of inquiries from industry, from individuals. The impact was, I don't have a number, but it's huge because just the amount of inquiries I get, I know people are interested in the project. That's the way I want to measure the impact.
There's this talk now about AI getting into different area of livelihood, whether it's in banking, finance, education, technology. How do you see emerging technologies such as AI or smart systems shaping the future of your research area?
I look at two sides. I got very excited when I see what AI can do, and I got scared too. At one point I was joking. I said, "Are we going to be replaced by AI or digital technology with AI or together?" So I normally treat that as one system because when you're talking about AI for agriculture, you also have to use the digital technology to go sort of hand in hand. The way I reviewed, it's going to have a huge impact on agriculture. Us as agriculture engineers, our job will be affected. Now, the way I want to put it is if you start now to learn how to use AI to your advantage, then you'll be okay. You'll be good. You're actually going to be doing better. But if you try to avoid it, bury your head in sand, you could be replaced by AI at some point. But I think the way it's going to work is as agriculture engineer, we actually will be sort of collaborating with AI. When you design something, old days, I guess you try different options, then you select materials, but it's very limited because every time you change something, you have to redo the calculation. So the design is an iterative process, right? It takes a lot of time to do it. The options you try, it's actually very limited. You cannot possibly try different combinations. Thinking about AI, if you design something, you want to change the configuration, or you're looking at the materials, what materials to use. You leave that with AI. You tell AI, say, hey, I want to achieve this. What are the options there in terms of the material or the configuration? The AI can actually do the quick iteration for you. Then use AI, you can actually save a lot of time, but looking at a lot more options, then eventually you can actually optimize your design as an engineer. Now, from the controlled environment point of view, AI definitely will change things. So at this point, if we actually try to control the environment, we set the temperature, humidity, or something else, or CO2. We think that's best for animal, for plants. But what do they think? If an animal can tell you, no, I don't like that. We can actually use digital technology and AI to actually sort of communicate with animal or monitor their behavior and use that actually to control the environment, not just based on our experience or based on our laboratory data to actually set the temperature. Even we have a good laboratory data to set the conditions for animal, but things could change. They may need different temperature in the morning than afternoon or day and night. So you can't possibly go there to adjust your thermostat every 10 minutes or half an hour. But if you leave it with the digital technology, and you can optimize. The other thing is farmer, if they try to run a facility, then they can sort of do a good job in looking after animals. But livestock farming actually is more than that. You have to look at the market, the feed, the pork price, all that. You have to put all that together. AI can help you to do that. Huge impact. We have to adapt, learn how to work with AI.
You said something about that. You're also scared about AI. What are your fears?
My fear is, as an engineer, if AI can actually design things, what we're going to do? We're going to lose our job. That's from the professional point of view. There's a lot of talk about, how the AI is going to replace humans. I believe, AI can replace some of our jobs. But if we learn how to work with AI, then we don't have to be scared. So we can actually take the advantage of AI.
So with this being said, what skills should young researchers in your field focus on developing?
Well, they have to look at the future, how the future is going to change in this particular discipline or in a particular research area. I saw some young faculty members when they started a job here, and they're so focused on getting funding and publishing papers. And I would say, yeah, give yourself some time and sit down to think about what you want to do now, what action is going to happen in your area, and then try to sort of looking at the long-term plan, and we're looking at 5 or 10 or even 20 years. That's very critical. I need to get my tenure, so I have to publish 3 papers this year. That is something it's important. I don't think that's a challenge. For most people now, publish 3 papers probably not going to be a big challenge. But you do have to look at the long-term development in your particular area. So that is one of the skills actually the young people would need. That's actually is the critical thinking. There's so much information out there, and how do you shift through the information or distill the information to actually find the real good stuff in it? So that's very critical. The other thing is probably communication, especially communication with farmers. In our profession, we need to talk to farmers to figure out what they need, to actually find out what are the problems out there. So that the communication skills, it's very important.
You said something about communication and also talking to farmers. What's the biggest challenge or barriers in terms of collaboration, whether within academic or even industry?
Yeah, there's sort of 2 types of collaboration. One is, you said, with farmers, with industry. The other one's with researchers from within or outside of your university community. Those 2 problems are a little different. Let's look at the collaboration with industry and the farmers. Now, that actually requires the researcher to actually know the industry, to know how to talk to the farmers, as I mentioned earlier. If you don't know the problems or the needs of the farmers, you cannot just work with farmers. And you're going to have to understand the needs there, and then you can work with them. Now, one of the challenges there is actually, I guess, the current system. You want to get promotion tenure, you have to publish paper. Now, sometimes working with farmers, you may not get a lot of publication out of it. You solve a particular problem. There's a balance you have to weigh carefully. Now, the collaboration with other researchers, that actually requires you reach out and then are willing to actually to spend the time, not looking for the return. Now, the way I want to put it that way is sometimes you talk to people and then, yeah, everything was good. And well, I guess you didn't get the money, or your group didn't get funded. So then everything stopped. You basically wasted all your time. But that you have to be prepared to do that, because not every collaborative project actually will end up with funding and the graduate students. Some actually, most of them probably will not, and some actually will. Then you have to be also open-minded. You have to know other industry or other research field. That actually takes a lot of experience, because what you're doing, maybe it's focusing on something in agriculture, but it could be applicable to other fields. When I was working on air quality in barns, then I was talking to people in medicine. They were talking about air quality, disease transmission in emergency rooms and ambulances. I said, oh yeah, it's the same problem. We're looking at airflow and the emission rate and how do you change all that? And we put in quite a few proposals together. Only one success a couple of years back. All the stuff I did earlier, put in the proposals, we didn't get funded. We spent time and effort, but there was not really much return. But return problems, it's invisible. Because of that collaboration, that sort of sets the stepstones for the future collaboration. Even you don't get money this time around, but there'll be other possibilities in the future. I'll give you an example. My air quality work, I work with Dr. Kevin Coombs from medicine, also Dr. David Levin in our own department. They're both actually microbiologists. When I was doing the airborne disease transmission, I don't know how to measure the virus, how to do the plating other thing. I went to talk to them. Now, this actually started with something I said earlier. We actually tried to improve the air quality in emergency rooms. I was working with people there. So that sets the foundation for me to work with people from medicine. There's opportunity, jump on it. And if it doesn't work out this time, or if you don't get money this time, but it's grown, then eventually it's going to lead you to some successful collaborative projects.
I know you've answered this question, but I just still want to ask it, just maybe in case you have any additional thing to say. How do you build trust and long-term partnership with colleagues across discipline? Because sometimes you feel, like you talk about publication, there's also individual interest. So how do you build that trust so that the other researcher would feel, okay, yes, this person also have my interest in collaborating with me and not just trying to use me to achieve their own goal?
The key here is it's willing to contribute and willing to spend time. Don't want to look at, okay, can I get something out of this project? No, that should not be your first consideration. You say, okay, this is an opportunity. I'm going to jump on it. I'm going to work with whoever who's interested in this project. I contribute as much as I can. If the project is successful, that's a return. If not, no return. That's fine. So you're going to have to sort of put that sort of return out of the picture first. And that's how you're going to build the trust. The other thing is you're going to have to find, people have different personalities, right? If you find two people on Earth, then there's a chance they cannot work together. You're going to have to find somebody you can talk to, can share the common interest. So that's how you're going to start. But the first, I think it's very important one that's willing to contribute and even to sacrifice in some cases.
Let's talk a bit about your students. I know you have graduated several students, PhD, masters, even summer students, and all this requires some level of guidance, mentorship. What would you consider the most important quality of an effective mentor?
Treat students as your colleagues and do not try to say, oh, you're the student, I'm the supervisor, you have to listen to me. And no, you work together on a project. This is how I learned when I was a graduate student, because I worked with my advisor at Penn State, Dr. Puri, and he just started his career here at Penn State. I started my graduate studies. So he treated me like a colleague. We wrote proposal together. So that's the way you should be treating your students. You work with them. Don't ask them to work for you. You work with them, or they work with you together to achieve the common goal. The other important thing is you have to be positive to your students. Sometimes, the student wrote a paper, it's not up to your standards. You can sort of tell students there's things to be improved, not to get upset. Oh, no, this is not good. Because training students, they got the potential there. You have to treat them equally as your colleague. Whatever it needs, you go to tell them. The other thing is sometimes the challenge in it, timelines. Some students actually cannot meet the deadlines. Sometimes you have to be firm. This has to be done by this date. So spending time on student work, it's very important. It's very time consuming if you review a thesis. You have to be very patient. They go through once, twice, 3 times, or 4 times, sometimes 5 times, to be very patient with students in terms of reviewing their work. It's not like you review a peer-reviewed paper and you said, okay, this is not good. You put the comments there, so rewrite. So for your students, I guess you have to sort of go step by step. Say, hey, how about this? And this could be a different approach or different discussion of a view on this. Because to them, it's a learning process. You're going to have to understand they're at a different level as you are. As a faculty member, you've gone through the graduate programs, you've been doing research, you wrote so many papers. You can see it, but students probably couldn't. But you have to point out the right direction and bring them up to the level they can see things as you see.
With what you're saying, it takes a lot of time and you're also working with deadlines. How do you balance this demand for research, teaching, mentorship, and administration? How do you balance everything together?
Well, when you teach, if you teach 2 or 3 courses, then you do all your research on weekends or nights. It's always a challenge for faculty members. It's not easy to balance. One of the things I learned is I don't take too many graduate students. So my number, normally I put up limits of 5 or 6. So I feel more comfortable if I actually taking 3 students on average. So then I can spend a lot more time. I don't want to take more students then I cannot spend quality time with them to review their work, to give them the right guidance. So that's sort of one of the philosophy I have followed. I try to limit the students probably 5, 6, at a given time. That's sort of the maximum. I don't want to have a dozen or 20 students, then I can't review the work. That's one thing I want to actually limit because I know the limit. Once you have done a course a few times, then it does not really require a lot of time. The research, I used to go to the office every weekend and try to catch up with research.
Let's talk a bit about teaching aspects. What has been the most rewarding part of teaching at the University of Manitoba?
I actually get excited when I go to the classroom. I like students' expression when you tell them why something happened like this, then this is the theory. They nod, or evaluation of your class, they put some positive comments there. That's very rewarding to me. For graduate teaching, then if you actually can convince somebody, or through teaching, not purposely, you teach a course and somebody learns something, then suddenly the person, oh, I want to dig into this thing. I want to do more research in this area. That's very rewarding too. That tells you something that's valuable to them. They picked up valuable stuff in your class. I think that's very important. I'm more looking at the outcome, how students actually, what they learned and how they will be using it. And especially when students come back 5, 10 years after graduation. So I was working on this project. I actually tried to find your class note and try to pick up that information. I said, oh, that's good. At least there's one piece of information that's useful. You still remember.
That's interesting.
Yeah.
With that being said, what teaching method have you found most effective in engaging students in biosystem engineering?
It depends on the type of courses you teach. When I teach a second year course or even third year, what I normally do is try to integrate the course content with some practical examples, like something happened in daily life. If you make that connection, then the students can actually follow you, especially some courses are very theoretical. Like when I teach solid mechanics, one of the most difficult courses undergrad students, sort of connect the complicated theory to some real life examples to do some demonstration if I could, show and tell with a little thing. When I was talking about the torque, and then also use the screwdriver as an example. How do you change your winter tires when you have to meet a certain torque requirement? Those are the things then they can relate the forces. What is it? I sort of give them the real life example. It gets better when you actually move to the third year with the lab. When I actually start teaching mechanics course in the third year, I develop new set of labs. Even sometimes I even ask a student when we test a piece of material to looking at the mechanical property. I said, well, if you have something you're interested in, some material which didn't even cover in the class, if you want to test it, see how strong the material is, bring it here. I guess one year the students actually brought quite a few bones from the farm. Hunting results, I guess. He brought it bones and said, let's try the question, see how much force we actually needed. Talking about the strength of the bone. And we do the lab and then said, yeah, test that. Teaching theory, it's boring. It's challenging actually to second or third year student. But if you sort of relate this one to some real life examples, and also to what they took previously, like in statics, and also how that connects. And then I'll also try to tell them why you're taking this course, where it's going to be used in the future. That's through some real examples too. So making the connections, integration, it's critical.
Generally, what has been your most memorable moment working at the University of Manitoba?
Oh, every minute. Not really, especially because I think all the stuff I'm doing since I started here, it's all interesting. I don't have the big moment in my career here. I don't have, something like build a $1 billion facility on campus. That's memorable. I was involved in a few large projects, but I said this is just part of my research. I do it every day. So that's what I'm saying. Every minute or every day, at least it's memorable in my 36 years of career at UFM.
Okay. So what advice do you have for young researchers in the department? People who are just starting their own career, what advice do you have for them, whether it's in terms of research, teaching, or administrative work?
Well, I talked a little bit about research, the long-term planning, and to look at the need of the industry, because our profession, our department is applied science to agriculture or biological systems. So you have to look at the needs of the industry. To be open-minded, willing to talk to people, to develop the collaborative research programs with other researchers on campus or even outside of the university. Everybody works hard. I don't have to give them that advice. Everybody try to publish more papers, so that they all know that. I think just looking at the long term, don't get buried in publishing papers. And sometimes you have to sit down to think about the future, to write down some notes, say, hey, this is what I want to do in 5, 10, 20 years from now. And thinking about what expert you're going to become. Would they call you or somebody else? The teaching part, actually, it's very difficult to give advice because everybody's got different teaching style, but connecting with students and integrating the course content with other courses and also with the practical application, especially, if you teach up-year design courses, you use your research experience and to sort of give students opportunity to look at the real world. Do that for my air pollution control course. So I give them older project I did, dust control, and they always get that as design project.
In terms of students, what advice would you give who are actually having setback in their research on how to handle failures as well?
Failure is inevitable. You always have a little failure, but as long as overall progress, it's upwards, you complete everything, there should not be issues there. People always learn from failure. But from students' point of view, they have to understand why they're doing it. If they just want to do it for degree, probably not worth it. If they want to do it actually for their own interest, they want to pursue something. Well, that's the real reason for going to graduate study. Maybe I should separate. I'm talking about the graduate students now. Because undergrad, it's more, we're talking about the teaching. And for graduate students, whatever whatever the project you're working on has to be something they are interested in. So there are some cases you have an ongoing project, a student sort of join your team, say, I want to do something in a slightly different area. Well, to me, if I don't have funding to support the student in that area, I always tell them, you have two options. You're going to be working in the existing direction with me, then you can get funding, get assistantship. Or if you want to working on project you selected by yourself, there won't be financial support. But I also want to tell them, I said, oh, this is actually a real example happened during my career. And the students say, I want to do this. And I said, oh, no, I don't have funding for this. But if you do this is the connection between the project. Eventually, you're going to learn the same principles. You're going to learn the same approach. It's probably just application. It's different. So then you think about it, you can make the final decision. Students actually are pretty happy. And he can now see the connection between his original thinking and the project he's working on right now.
Thank you so much. With all you have done, both in the university, outside the university, and globally, what legacy do you hope your research and teaching would leave?
I don't want to leave any legacy. Everybody contributes a little to the knowledge and the development of the technology. I'm just a little tiny piece there. Whatever I contributed, if people could use it, great. I didn't even realize yesterday I met with a person who's doing some work actually on disinfecting barns. And I don't know how she actually finds some papers I published earlier. And she called, how about if we do this? This is the things you never know. I don't have a particular thing. I don't break in contribution to the science or to the technology, but I make my little contribution to the industry and to the research, to the knowledge. That's the way I want to be remembered. Or not remembered at all.
Thank you so much. So what do you look forward to doing after retirement?
I don't have a plan. That's probably the best plan. I will be for the next few years. I still got graduate students to complete. So I'll be staying active in doing research. Sort of agreed to give some guest lectures in December. So I'll be here for a bit. Bigger plan probably is to get more involved with international collaboration. I'd probably be being part of the big projects, but not leading anything. Retired professor. I can give advices and other people can do the job.
Yes.
Yeah, I don't want to sort of PI of a project. So that's before retirement.
So is there anything you'd like to say to the Department of Biosystems before you retire?
Not really. The department's doing so well. It's got the right direction. It's got right compositions of expertise. Keep doing the good thing. In the future, if there's opportunity, hire good people in the promising areas. I like this department because the whole environment is it's like family. So everybody work together and talk to each other. That's how the department should be operating. Keep up that good tradition.
Thank you so much, Dr. Zhang, for generously sharing your time, insight, and incredible journey with us. It has been a true honor speaking with you. As you transition into retirement, your enduring influence will be reflected in the generations of students you have guided, the colleagues and community you have inspired, and the lasting contribution you have made to agricultural engineering and education.
Well, thank you, Uduak. It's been a pleasure talking to you, and it's been a pleasure working with you in the past, too.
Thank you. Thank you so much. And thank you all for listening. And please stay tuned for more upcoming podcasts on the University of Manitoba's Resources for Agricultural Engineering, your gateway to discovering latest innovation, research, and practical solutions in agricultural engineering. Thank you.